I would like to welcome everybody back. What we're going to be doing is continuing on with our discussion about how science is conducted. And the first thing we're going to be talking about is minimizing bias in experimental design. Something to keep in mind is that everybody has opinions, even scientists. Really, especially scientists. And many people are guided by their opinions, but scientists cannot really do this, at least not in their work. Now, our opinions can help us form hypotheses and theories about what's going on and about what we're observing, but when it comes to testing our theories, it has to stop there. If a scientist's opinion influences their interpretation of the data, then the scientist may reach a conclusion about that data that is wrong. This is called bias. Now, one way to get around this is to conduct a blind experiment. This is where the individual subjects are not aware of what they're getting. So in our case, the subjects with the colds do not know they are getting vitamin C. They have just agreed to get a pill, just some sort of pill. They don't know what it's going to be. You know, maybe they filled out a questionnaire that says, are you allergic to these 50 things? And vitamin C was in there. So we know that it's safe giving them vitamin C, but they do not know they're going to get vitamin C. Now, to further prevent bias, a double-blind experiment could be used. Now, in the double-blind experiment, the researcher does not even know what he is giving them. So let's say that I am the lead researcher on this entire project, and I've got all my technicians, and I am worried that if one of my technicians hands somebody a vitamin C pill, and they know that it's a vitamin C pill, that their facial expressions or body language might give away that this is going to make them better, like they're real happy. And the people with the sugar pill get handed the vitamin C pill and they're really sad. And then, you know, these are the people who are also going to be doing the analysis on it. So I'm not really going to participate. So the people who are giving them the stuff, you know, they are unknowingly, they don't know what they are giving them. Maybe one bucket's got a 1 on it, maybe one bucket's got a 2 on it, but they just hand them the vitamin C and they give them the sugar pill and they don't know what they're actually giving them. What I've just described would be the ideal way of doing it. However, we cannot necessarily use this method all the time, primarily because of ethics. You know, not giving somebody vitamin C would not be that big of a deal because, you know, some people take vitamin C and some people don't. But let's say that we want to know what the best teaching method is to use on grade school children. Okay? For a double-blind controlled experiments, we would have to purposefully not educate some students, or maybe use something that we think or know is bad, and educate them in a way that would be counterproductive. Okay, it's completely unethical. And so, you know, as scientists, we have to be aware of this and make sure that what we are not doing, that means sometimes we're not able to answer the question using the best method. So in those cases, we might be looking for some sort of correlation. Okay, again, let's go back to our cold example. It's believed that being under stress can cause a cold to last longer. Well, it might be considered unethical to purposefully stress people over a long period of time. But, you know, we could observe people who are under stress and then record the length of their cold. I mean, think about, you know, just yourself at test time during finals week, or maybe you haven't had finals week yet, but believe me, it will be stressful. You know, maybe we can observe the length of time that colds last during finals week compared to the first week of class when you're not really worried about anything. You're just getting syllabi and taking a couple of lectures or something like this. There's no test yet, and looking at the duration of colds in these two different periods. Okay, but what you've got to remember is that correlations does not necessarily equal causation. You might observe a correlation between stress and the length of a cold, but that does not mean that the stress level is the cause of a longer cold. It could be, but that is not necessarily the case. This is why you'll hear the phrase, correlation does not indicate causation. But again, it may be a good place to start with developing a hypothesis. So I observed this, I noticed this correlation. Now I'm going to start developing a hypothesis on this. So let's stop here and take a quick break. And when we come back, we will continue on with our discussion. I'd like to welcome everybody back. What we want to talk about now is science and statistics. We've completed our experiment, and we have some data on the duration of colds and vitamin C. To objectively examine what our data is telling us, we're going to use statistics. For the most part, science cannot happen without statistics. Why? Well, if we relied just on our powers of observation, it would be very easy to misinterpret the data, especially if we don't look at it objectively, which can easily occur, even if we're very well-meaning. And remember that, as I said before, scientists have opinions. And that may actually be leaking into our interpretations. So, we see a group of numbers and we say, oh, well, this group of number appears to be higher than this number. Okay? Statistics are a tool that lets scientists look at data based on math. Now, there are several components to your research project that you will need to examine your data with statistics. First of all, you've got to remember that when we are looking at the effects of colds in people and so forth, we may have only selected 100 college students to look at. Okay? What we did is we took a sample of college students, or we took a part of the population. So we took a sample, which is a part of the population, that we tested our hypothesis on. Okay? We didn't take everybody and test this. Okay, we only took a sample. We collect data points on the amount of vitamin C that is given and the duration of the cold. To start analyzing the data, we might calculate the mean or the average for the duration of a cold for the people not given vitamin C, and the mean and the duration for the cold people given 500 milligrams of vitamin C, and the mean for the duration of the cold for people given 1,000 milligrams of vitamin C. These means or averages are great, but what happens if the means are close together? What I mean by this, and not mean in that respect, but anyway, let's just say that the duration of a cold for people not given vitamin C was 24 hours. And the duration of the cold for people given 500 milligrams of vitamin C was 23 hours. Even though we randomized our subject, used controls, and gave them vitamin C using the double-blind method, we still don't know if the difference between the duration of the cold between people given no vitamin C and people given the 500 milligrams of vitamin C was just due to chance or just dumb luck. So what if just by accident that the people in the no vitamin C group had super immune systems? Now, this is not likely because we randomized, but it's still possible. To help us with this interpretation, we calculate the confidence intervals for our means. Essentially, once we have calculated these, we can then look at them on a bar or some other type of graph to look to see if these confidence interval bars overlap. So if we're looking at something that's 23 hours and 24 hours, there's a good chance that the data that we're looking at is what we would call not being statistically different or statistically significant from each other. Okay? These confidence intervals can allow us to look at how variable the data is. So if the vitamin C taking subjects in our test had colds that lasted for 10 hours, 30 hours, 34 hours, 22 hours, and so on. So each individual, okay, so remember we measured it in the individuals. And this person's cold lasted for 10 hours, this person's cold lasted for 30 hours, this one's lasted for 34 hours, this person's cold lasted for 22 hours, and so on. That's a lot of variation. And consequently, our error bars would be wide. The wider the error bars, the greater the chance that they will overlap and will not be considered statistically different. If our vitamin C subject had colds that lasted 22 hours, 23 hours, 23.5, 23.1, and so on, then the duration of their cold would have a much smaller variability and shorter error bars. Now, don't worry about having to calculate how to create these error bars. Okay, you're going to learn that in statistics, but and maybe you're not taking statistics. Maybe your program doesn't require that. But when you look at data, you have to keep in mind that that is a fairly important aspect of the results. And that's what that means. And so, if you've got this mean that is a little bit lower than the other mean, so the mean of no vitamin C and the mean of and vitamin C, and they're really close together, like 23 and 24 hours. Okay? If there are no error bars or some other indication that measures how variable people responded in those colds, you're not going to know if those are really different or not. Okay? So, you can see here where we've got it. If these two error bars are overlapping, this data is probably not going to be different from each other. It's not statistically different from each other. You may look at it and go, well, that's 23 and that's 24 hours. That is different. If the error bars are overlapping, then that's not different because our error is large enough that we don't know what's actually going on. If we have an example where the duration of colds is 15 hours for people who took vitamin C and 24 hours for people who did not take vitamin C, even if we have fairly wide error bars, you can see that this data is probably different from each other and that there is some sort of effect. So if things are very wide apart, you can make the assumption that they're probably different from each other. But anytime you've got data that's very close together, like we just talked about, 23 and 24 hours, you're really going to need statistics to tell you if those are really different from each other, at least numerically or statistically different from each other. So, the important part of this is just by looking at these averages or these means, that does not tell us much. We have to use additional statistical tests to understand what the data is telling us. And this just scratches the surface, and it's not a very deep scratch at that. Just know that without statistical analysis and the various tests that are available to us, it would be nearly impossible to discern meaningful information from the data that we collect. Now, these statistics will only tell us if the data is different from each other. They do not tell us if this difference is important or not. So, with our example, do you think it's worth taking vitamin C if on average your cold will end 1 hour earlier. So let's say that we looked at our data and colds end at 23 hours of vitamin C, and our other one is colds last 24 hours if we don't take vitamin C. If a bottle of vitamin C only costs $1, it may be worth it. I mean, really, you got a cold. When that cold's over, if it's over an hour earlier, it may be worth it for $1. If that bottle of vitamin C costs $20, I'd probably just tough it out. What's another hour? So ultimately, it's up to the scientist or the consumer or whoever to determine if the results is actually significant in terms of the question you're asking. Statistics just tell us if our results are due to random chance or not. Okay? So just keep that in mind. The interpretation is up to the scientist. Statistics tell us what the numbers, what they're doing, and if they're really different from each other, and other factors like that to help us make a decision. You also have to remember that statistics are just a tool to analyze data. Statistics cannot tell you if the project or the research was set up correctly. That's why we talk to other scientists to help us determine if we're going about our project properly. Then, in the end, we write up the results and send them out for publication. Other scientists who are experts in the field will evaluate our study design, our use of statistics, and our results to see if they agree that the research was carried out properly. If they agree, then typically, this research will go ahead and be published in a peer-reviewed scientific journal. Now, the peer review part assesses what the other scientists did. But does that mean that our conclusions are the truth, or are they correct? Not necessarily. Okay? But for the conditions that we worked under, and if we reported them honestly, and we described the subjects that we used properly, and our peers have determined that our procedures were correct, then for those conditions we just described, that is what happened. But additional research may come along and eventually disagree with what we have done, and so maybe they get different results, and then we have to determine, well, was their research better or different than mine, or did they make a mistake? Or somebody else could come along and do additional research and provide additional support for our results. And so it's a never-ending process, but ultimately that's how science progresses. So this is why a lot of times you're going to hear in the media that, in 1 year, vitamin C, scientists have shown that vitamin C is great for reducing the duration of a cold. And then, a couple of years later on the Today Show or on ABC or something, they say the exact opposite, that science has shown that vitamin C does not affect the duration of a cold. And you're thinking, well, wait a minute, I just saw on the other program a couple of years ago that vitamin C is great. And this is what makes people pull out their hair and think scientists are full of crap. But, it is really because this process is changing. The other thing that the news may not report is after that first study, maybe there were 50 more that showed that vitamin C reduces the length of a cold. But this last study that they latched onto, maybe these scientists were trying to find the minimal amount of vitamin C that would reduce a cold. Or maybe they were looking at the vitamin C in kumquats, and maybe there's just a tiny amount of vitamin C in kumquats. And the scientists knew this, but their results were misinterpreted by the media. So that's why it's very difficult to rely on the media for scientific information, because these people a lot of times aren't scientists, and if they don't have somebody carefully review the data they're looking at, and if they don't know about all the other science that's going on, they may not be able to put it in perspective. And what they should have said is that this report came out today that said the 10 milligrams of vitamin C that's found in kumquats does not do anything to reduce the duration of colds. But what they haven't done is told the rest of the story, that the 50 studies done in the 5 previous years show that vitamin C, if taken above a dose of 50 milligrams, can reduce colds anywhere from 30 minutes to 2 days. So that's why people will get frustrated and don't understand what's going on. But oftentimes it's because of the continuation of the scientific process, and not all the details are related in a 10 or 20 second soundbite. You got to remember, at one time, most people thought the world was flat, or that everything revolved around the earth. And they thought this was developed through the scientific method, and it probably was for what we had at the time. But, as science progresses, so does our knowledge about how these things actually work. So, what do we actually know about vitamin C and colds? Because I've been talking a lot about potential experiments that could be run, and experiments that have been done on vitamin C, and what we're doing is thinking about vitamin C in terms of that knowledge that our parents have passed down, and our grandparents, that wisdom that they have told us that, you should take vitamin C, and a cold will be shorter in length, or you won't get colds as much, or in all honesty, there's an awful lot of science that's actually been conducted on, does vitamin C reduce the length of colds, or the severity of colds, or the duration of colds? And in general, the conclusions that they have found is that vitamin C doesn't really affect the length of colds or duration. There are some instances where the science has shown that people might get fewer colds if they take vitamin C. But again, remember, it goes back to that idea of what is important to you, or what's significant. Do you want to spend the money to constantly take vitamin C, but it only reduce the number of colds you have, or number of days of colds you have, maybe by 1 day a year, and maybe over the length of the length of a year, maybe you spend $100 on vitamin C? Most of the research, or some of the research at least, shows that if you take vitamin C once you have a cold, it really doesn't do much at that point, because it's almost too late. You need that vitamin C there so that your body can have ready access to it when it actually gets infected. So again, this research on vitamin C is ongoing. A lot of the papers I found were back in the 70s, and actually there were books already written on vitamin C and colds back in the 70s. And even today, in the mid-2000 teens, research is still ongoing about vitamin C, because they haven't reached any hard and fast conclusions. But the current thought is, or the current consensus is, that it really doesn't have a huge effect. And I would think pretty much most scientists who work on this would say it doesn't have a significant effect. It's not like you can take vitamin C and the number of days of cold. So, think about this in terms of how many days do you have a cold each year. So some people might have 23 days of cold each year. So your nose is runny 23 days a year, okay? It's not like you can take a certain amount of vitamin C, let's say 500 milligrams or whatever, a day, and the number of days of colds that you will have will be reduced to 2 from, say, 23, okay? That level of vitamin C might reduce it by a day or 2, or maybe by a half a day. It just depends on the research and the conditions that were going on. So even though it may have an effect, it may not be a significant effect. So again, all of this is available in the primary literature, and then is interpreted on various websites in secondary literature. And we'll talk more about that later on. So let's stop here and take a break. And when we come back, we will continue on.